7-8 is about probability. The required sections here, number 1 and number 2, I'm very literal and when I say write out the example with its solutions, explaining the steps in your own word. You will find them in your book. It's page 403. I'm not actually even going to do that required section for you. I want you to look in the book and kind of figure it out. I will go through some extra other notes with you. So the first thing is I'll call them time problems, time probability. And basically just know if it's a time problem, it tells you so many seconds of this, so many seconds of this, so many seconds of this, or minutes, or hours. It's the time of what I think they call it favorable. Out of the total time. So let me give you an example. Lucy was expecting her first child. It could come, and maybe a better way of saying that is she could go into labor at any time. Her husband works and is not home between like traveling to and from work. We'll say 10 hours per day. Find the probability. Whenever you see a capital P, that's probability that he is at home when she goes into labor. Well, they're talking about days here, so we're talking out of 24 hours. He is home. If he's not home for 10 hours per day, he is home for 14 hours per day. And that reduces to 7/12. You may leave it as a fraction, or you can change it as a percent, whichever you prefer. I happen to not be sitting here with a calculator, so I'm going to leave it as 7/12. There's a 7/12 probability, a little better than half, that he will be at home when she goes into labor. Example 2 is this kind of problem where you just have to figure out how much time total they're talking about, like in the cycle. For this cycle, the cycle was a day, so 24 hours. The story problem that's in example 2 is about a bus stop, and it's a 25-minute cycle because it's a bus going by every 25 minutes. I think the problem in the homework has to do with a traffic light cycle, and the different traffic lights have different cycles. So they have different total number of seconds in their cycle. All right, so the other type of probability problem they're going to give you is geometric probability. And with geometric probability, I'm getting a little ahead of myself here. It typically has to do with targets. So I'm just going to say the area that's favorable out of the area of the target. So let me start with a pretty easy one. I'll do a couple examples. So example, I have a circle target. We'll say it has a radius of, I don't know, 12 inches. Inside that, somewhere, I have another circle. Let's see if that's 12. This has a radius of like 3 inches. And basically, if you hit the target randomly, find the probability of hitting this little red circle, right, of somehow being in there. So the first thing you should realize is that it's not 3 out of 12. So don't try to think that it is. You have to actually find the areas. The second thing to notice is that you should be able to kind of estimate how much you think it is. Like, even looking at it, you know it can't be 3 out of 12 because that would reduce to 1/4, and more than 4 of those circles would fit. My drawing isn't super perfect. In the book drawings where they're more accurately drawn, you could get a better estimate for how much it should be, but it should be kind of obvious that there's no way that that's 1 out of 4. So in order to find out, I need the area of the favorable. In this case, my favorable thing, what I'm trying to get is the red circle. So I have the area of the red circle. And that would be pi 3 squared, or 9 pi square inches. I also need the area of the target. So I am ignoring whatever's inside. Sometimes that's confusing to people. When I say like the area of the total target, they try to take the 2 circles and add them together. No, the total target is just like the big shape. In this case, the outer shape is a circle. So that's what I'm finding the area of. And that would be pi 12 squared, which is 144 pi. So put together, that'd be 9 pi out of 144 pi. That reduces. The pi's cancel. And they also both divide by 9. This comes out to 1 out of 16. Once again, you can turn it into a decimal. What this is saying is 16 of these little red circles would actually fit inside. Like I said, mine's not super accurate, but you can see that there'd be a lot when you take all the little pieces out. So that is the probability. Some of these problems with geometric probability are a little bit easier than that because sometimes it's obvious how much is shaded. So for instance, if I took a square and I took it corner to corner and I filled that in, you should be able, without actually determining the areas, that is obviously 1/2. So on the problems where it's obviously 1/2, know that it's obviously 1/2. The other problems that come up all the time, every time there's geometric probability, they do these problems. It's circles inside squares. You should really know, kind of file away, the percentage. Whenever you have a circle inside a square like this where it's touching the corners, what percentage does it look like that it is? It's pretty high. I'll go ahead and figure it out for you, but you should just know and kind of just know that that's always the case. It doesn't really matter what size the square is and what size the circle is, because if it gets bigger, it's just still the same percentage. But to make it easy, I'll go ahead and stick one in. We'll say that this is 1 foot, which means the size of the square is 2 feet. So the shaded area is pi 1 squared, which is pi. And the big target is a square, so it's 2 squared, which is 4. So it's pi out of 4, which is a little bit more than 75%. I'm trying to think what it is. And once again, I'm not sitting here with a calculator, but it comes up all the time. So give me a moment. It is approximately 79%. So what we're saying here is that inside the circle, inside is 79% of the area, which means, by subtraction, outside the circle is 21%. These problems come up often enough that you should pretty much just know that inside the circle is 79%, outside is 21%. And it doesn't matter if they do something weird, realize that this is the same problem. Right? They just took the circle and put it in weird places. Right? They cut it in half. Still in the circle parts is 79% and out of the circle parts is 29%. Anyway, based on this, see if you can work through those examples. Do the required parts of the notes, which are up here. Example 2 and example 3. Example 2 is really easy. Example 3 is a pretty tough example, but I think you should be able to walk through it based on what we talked about.